sector. Okay, so Mr. Wang, please.
Hello everyone. My name is Wang Yan, a PhD student from Department of Chemistry, and my supervisor is Zhu Zonglong. It's a great honor for me to deliver a speech here, and today I'm going to talk about how to fabricating efficient and stable polymer solar cells based on vanillin linker-based polymer acceptors. So my speech consists of 3 parts. Let's move to the first part. As we all know that solar cells is a promising green technique that could generating electron energy from solar energy. And a typical structure is listed in the left part. The p-type and n-type semiconductors are sandwiched between 2 electrodes and could generating electrons and their photoilluminations. And the most important part of the solar cells is the p-type and n-type semiconductor materials, and we call it active layers. For the organic solar cells, it has a lightweight, large area, and semi-transparent flexible device advantages compared to the typical silicon solar cells. And for the polymer solar cells, the most important part is the N-type polymer acceptors, which limited the efficiency of the polymer solar cells. And several typical acceptors are displayed here. And thanks to the Y6 based acceptors, the PCE is close to the smallest molecular acceptors solar cells, and it has great strengths in morphological stabilities, mechanical flexibility, and large-scale fabrications. However, it still has great limitations in the PCE comparing to the small molecular-based acceptors. Here, for instance, the L8BO is one of the most efficient small molecular-based acceptors. And the PY2FT is similar structures that comparing to the L8BO. So they can all combine great with the donor polymer PM6, but the PCE for L8BO is around 18.2%. However, when using the PY2FT, the PCE is dramatically decreased to the 15.2 PCE. So the fill factor is decreased really a lot from around 80% to 72.6%. So the key factor in the polymer solar cells is how to increase the fill factor that close to the small molecular-based acceptor solar cells. So how to improve the fill factor in polymer solar cells? It could orient from the device mechanisms. It needs such high hole and electron mobilities, and the excitant dissociation should be as much as possible high. And we want the excitant recombination could be surpassed as of course the series and short resistance is also important in the solar cells device. But these things could also oriented to the device morphologies, such as the stacking probabilities for the donor and the acceptor materials, and the blend form film morphologies. And these 2 parts, we need to design great polymer donor and polymer acceptors materials, it could increase the staking probabilities of the blend film morphologies. And also, we could use some device fabrications tricks to improve the blend film morphologies, such as the beach disc, the bulk heterojunction structures. It's an efficient structures we usually use in the organic solar cells. However, it's not such ideal structure because it will increase the recombination constant that we want to decrease for the efficient polymer solar cells. So let's move to the next part. So we here designed a vinylene linker-based polymer acceptors to have a better packing probabilities. So the PYV gamma is our target molecule, and the PYT gamma is compared structures that published in the previous work. So after we use a vinylene linker here, comparing to the ethylene linker, it shows great covalentarities because the decreased from 22 degree to 0.2 degrees, and also it shows great symmetries as C2V symmetries comparing to the silicon linker, because it breaks the symmetries in the polymer backbone, and also the degree here between two repeated units is 0, and it could form parallel backbones in the long chain after deposition to the film. So we think that vinylene linker-based polymer acceptors have great advantages for the molecular packing, and it should increase the electron mobilities, which is really great for the our polymer solar cells. So then we characterize the film morphologies of the vinylene linker-based polymer acceptors compared to the PYT gamma. So as you can see, it slightly increased the packing in the neat film morphologies, and also it shows better favorable morphologies compared to the PYT gamma. So it could increase the hole and electron mobilities in the blend film device here, and the better hole and electron ratio is really important for the PCE increasement in the device. So here we fabricated two devices that PM6 and PYV gamma, and PM6 and PYT gamma. So after optimization, the PCE of PYV gamma is 17.1%, and while the PYT is 16.1. So usually the VOC and GSC parameters are trade-offs that we can talk that the PCE increasement is oriented from the field factor part. It increased from 71.9 to 75.8. And also the EQE response is increased in these regions, and it could be attributed to the lower defects in the blend film morphologies. And also the PYV-gamma performs better thermal stabilities than PYT-gamma. So this work is published in the Advanced Materials. And move to the next part. We want to use some fabrication techniques to improve the PCE. Here we use that sequential depositions where xylene. So the typical spin coating technique for the solar cells is use one-step blend coating that we dissolve the donor polymer and acceptor polymers in one solution, such as chloroform. And here we use that sequential depositions that use two steps. The first step, we use the donor polymer solved in the xylene and deposit the PM layer first. And then we use the acceptor solutions to form the total pseudo bilayer structures. So the most strength of the pseudo bilayers comparing to the BHG structures, it should have a slight graded structures that have more donor domains close to the P dot PSS, HTL layers, and more acceptors close to the ETL and silver electrode that is more efficient for the charge collections. So then we first compare to the chloroform chloroform solvent, because the boiling point of the xylene is higher than the chloroform, so it will form better pre-aggregations in the xylene. As you can see, the PIV where xylene and xylene TA, it shows a redshift for the peak and increased optical densities. That means it could absorb more light in the film formation. And also comparing to the blend coating, one-step depositions and sequential depositions, it also showed a slight increase of the PLV part. So we think that the sequential depositions is available in the polymer solar cells. And also the blend film morphologies of the SD-based device, and it's also better than the BC-based device because the AFM shows a great fiber-like structures. And also the packing from the GX part is also great than the BC-based device. And here, after great optimizations, the BC-based device achieve a decent PCE of 16.6, and SD-based device achieves a marvelous PCE of 17.7, which is one of the most highest efficiency in the polymer solar cells. So the fill factor is improved from 75.8 to 77.7. And also the VOC and GSC is slightly increased. So we summarize the polymer solar cells efficiency versus fill factor here. So then we try to analyze the which part could lead to the efficiency enhancement. Here we use total energy analysis here to orient each part of energy loss. So the transmission loss is ascribed to the EG of the polymer and donor and acceptor materials. So they are the same. And the non-absorbing and AQE loss is related to the absorption and AQE. So and we can see that the carrier dynamic loss clearly expressed here. As you can see, the purple part. Yeah, here decreased a lot. So we think that the FF loss is really important here to investigate. And firstly, we use the FF max calculations to see how to see the limitations of the highest field factors in the device, and the formula is listed here. So after calculation, that the FF max of the SD device is 86.2 compared to the BC device 85.8. So the most decreased part is charge transport loss here, and so the charge transport process is really important here. Thus, we need to orient which part of the charge transport is efficiently decreased here. So we separate the FF loss parts into three parts. The FF drops from series resistance and shunt resistance, and also the J02 recombinations loss. So here the FF drop from the series resistance, the first part contains the most part of the field factor loss. However, this part of SD device and BCD device is closed, and the shunt resistance caused field factor loss here. For SD-based device, is clearly dropped from 2.0% to 1.3%. So the shunt resistance increase should be the key point in the SD-based devices for polymer solar cells. So we also fabricated the flexible device of the polymer solar cells, and the SD-based device also shows better efficiencies and stabilities comparing to the BC-based devices. And here are the structures of the flexible polymer solar cells and the photo image. We can see that the PCE remains around 94% after the correctional radius decreased to 1 mm. So we think that active-based performs better mechanical stabilities than the BC-based device. And also, we characterize the thermal stabilities and photo stabilities of the BC-based device and SD-based device. And also, you can see that the SD-based device shows better thermal stabilities and photo stabilities here. And this work is under review in the advanced energy materials. And thank you very much for listening.